Hello everyone, my name is David Din. I am a sales engineer with JuliaHub, and today I'll be talking about modeling, simulation, and control in JuliaSim, hoping to give you a taste of both our graphical and our code-based interfaces to JuliaSim. So we'll start off with seeing how we can create a model and simulate and analyze that model. Then we'll move on to linearizing the plant portion of our model to allow for control system auto-tuning and optimization. Then we'll go ahead and discretize the plant and controller in time so that we can implement a digital controller, which will enable software in the loop validation. So to start off with, we'll have a blank canvas inside of JuliaSim, and I'll show you how we can build up a component from scratch. And in this case, what we'll do is we'll build up a mass spring damper. Once we have a feel for that, we'll take a look at our more complex model, which is the active suspension system. If we look at the right side right here, we have a visual representation of that system. It's basically just a vehicle that's moving over a road. So here, as part of the model, we see we have road and road data, which is giving off a signal that we see to the left side right here. The road is mostly flat, except for it has one bump in the road as the vehicle moves over it. On top of this road, we have a vehicle, which is represented as a seat, suspension system, and a wheel. And out of this vehicle, we can pull the seat position signal, as we see on the left side right here. We can see that the seat position begins at 1.5, and as it moves over the bump in the road, we have an oscillating response for the seat position. Additionally, we have a PID controller in the loop here, which is controlling an actuating force being applied on the seat in an attempt to dampen the seat response. And of course, is attempting to dampen the seat to the reference value of 1.5. After that, we'll turn our focus to the controller inside of our system, which is the PID controller. And what we'll do is we will attempt to auto-tune or optimize this controller so that once again, the seat position tracks the desired reference position of 1.5 as closely as possible. Okay, so with that, let's go ahead and get started. Right here, I am on our JuliaHub cloud platform page. We'll be starting off in the JuliaSim GUI interface right here. And then in a few moments, we'll move on to the code-based interface right here, JuliaSim Studio. Okay, so I'm gonna go ahead and start up JuliaSim right here. Here we're greeted with a welcome page. We can go ahead and open up an existing project or create a new project right on the right side. So that's what I'll go ahead and do. And projects side of JuliaSim or encapsulation of models inside of JuliaSim, meaning they contain all the information needed for both graphical and code-based representations of the model. And these projects are backed up as Git-based repositories on our cloud platform. Okay, so before we start doing anything, let's go ahead and orient ourselves with the interface here. Right in the middle here, we have our workspace area. Later on, when we have models open, we'll be able to see their schematics right here in the workspace area. Along the bottom here, we have our simulation panel. When we run analysis in a moment, we'll be able to see the results of those analysis in the simulation panel. And then finally on the left side over here, we can see that we're currently on the library tab, and we have two libraries already loaded into our project. First, we see the standard JuliaSim modeling language library in here, and also the library that we just created specifically for this project. Okay, so now what we're going to do is create a mass spring damper. What I'm going to do is I'm going to import some standard libraries to help me do that. So what I'm going to do right here is I'm going to import in block components, JuliaSim example components, and translational components. I can see those libraries populate on my left side right here. What I'm going to do is expand my demo library, and I'm going to click on Add a Component. So now we see we have a new component in our library, and that component's schematics now being shown in the workspace area. And of course, that schematic is just blank right now. So the first thing I'm going to do here is I'm just going to rename my component here by expanding the parameters panel, and I'm going to give it a name of mass spring damper. Okay, So now I can start building up my component. The first thing I'm going to do is I'm going to give my mass spring damper two flanges, in other words, two mechanical ports. And these will be used to allow us to connect this mass spring damper onto other components later on. Now that I have those two flanges, I'm going to add in a mass block right here and also a spring damper, making sure that I keep all making sure that I complete all these connections. Okay, so now that's it. Now we have a mass spring damper component. We can think of it like this, and we can use this component to build up more complex models in a component-based approach. The idea is this mass spring damper can be connected to other components at these flanges or mechanical ports. Okay, so now that we have an idea of how we can build up a component from scratch, let's go ahead and take a look at the more complex model, the active suspension model. So on the left side right here, under JuliaSim example components, I'm going to expand this library. There I can find the active suspension model. And what I'm going to do is I'm going to make a copy of this model and place it in my library so that I can perform analysis on it. Okay, so now I see I have an active suspension model inside of my library that's being showed on the workspace right here. What I'm going to go ahead and do is I'm going to rename this active suspension model so that we can, so that I don't confuse it with the standard model I copied from. Okay, great. So what I'm going to do now is I'm going to select the Analysis tab, and I'm going to add an analysis under the My Axis Suspension model. And the analysis type we want to add here is a transient analysis type, because what we are interested in is the seat response over time as it moves over the road. I'm going to go ahead and click Add right here. You can see my simulation panel is populated with a transient analysis for My Axis Suspension. I'm going to go ahead and click Run right over here. And in a moment, when the result or simulation is done, we'll be able to plot our result right here in the results tab. So what we're doing right now is we are running the simulation with the standard default values. Particularly for this PID, all the gain values for this PID controller are using the default values. So let's take a little closer look. So I'm going to select this PID block and expand the parameters panel on the right side right here. And I can see that my KP, KI, and KD parameters for my PID controller component are already set, and they are currently set to these three default values. So now they're currently using the default values. We can see if I expand this drop-down menu, I can choose any of the default values, or I can specify my own custom value for this PID controller. So if you're wondering where these default values come from, it turns out that the PID block is able to inherit from its top level My Active Suspension block. So what I'll do right now is I'm just going to go ahead and click somewhere in this blank canvas. And I can see my parameters panel right here has now changed to My Active Suspension parameters. And if I scroll down, I'll see right down here that we have the three default values for P, I, and D. And this, of course, is what the PID controller is inheriting as its default values. So if you want to change the PID gains at any point, we can either change them right here at the top level component, which will change their default values, or you can instead just go ahead and click into the PID block and set your own custom value right there. So I'm happy with using the default values right here, so I'm just going to go ahead and leave it as is. Looks like our simulation has finished up, so I'm going to go ahead and plot some of the variables from our simulation. What I'm interested in plotting is the force that the road is applying on my wheel, the force that the actuator is applying on the seat, the actual seat position signal, and the resulting error signal from that. Okay? So these are the four things we're going to plot right now. So I'm going to expand this, and I'm going to go ahead and create a visualization. The type of visual, I'm going to plot the road force right here. Also going to plot the force from the actuator, the seat position, and the error. Okay, so now that we can see that these have been plotted, let's just take a closer look. So this right here, we can see that this is the amount of force being exerted on our vehicle by the road. Here's the force being exerted on the seat by the PID actuator. And of course, as a result of these two forces, we can see that we have a seat position signal pulled out of that. And of course, the error signal is going to look pretty similar to the seat signal because the error signal is simply the seat signal minus 1.5. Okay, so now let's say we're looking at this and we're saying, hey, well, I really want I want my PID controller to keep my seat position as close to 1.5 as possible. In other words, keep an error level as close to 0 as possible. So what we could do right here is we could go into this PID block and modify the gain values until we get a seat response that we like. That would be somewhat time consuming. So instead, what we're going to do here today is we're going to show you how we can optimize this PID controller using JuliaSim. And for this portion of the demonstration, I'm going to go ahead and move over to our code base interface. But what we're going to be doing in that project from the code base interface is we're simply going to be analyzing and linearizing this exact same model that we just did right here inside of the GUI. Okay, so this active suspension model, we're going to pull the same model and analyze it inside of our code base interface. So I'm going to move over to the code base interface right over here. Right now I have a project that we've created ahead of time. And this project, what it does is it takes that same active suspension model that we just saw, and we're going to do some auto tuning on the controller portion of this model. Okay. So what I'm going to be doing is I'm not going to be talking through every single line of code here, but I'll be talking through things at a high level. Okay. So the very first thing we do right here is, of course, bring in that active suspension model for analysis. The second thing we're going to do is we're going to linearize the plant portion of the model. And the reason we do this is so that we can more easily analyze and design a controller for this model. So here I've plotted the Bode plot for the linearized plant so that we can kind of understand the phase and magnitude responses with respect to frequency. Okay, so now that we've linearized the plant, what we're going to do is we're going to set up a nominal, in other words, non-tuned, non-optimized controller. So this is just the default controller, and we're setting it up because we want to compare the performance with the nominal controller against the optimized controller that we'll see in just a moment. So the next step here is we're going to set up the auto-tuning code to optimize and auto-tune that PID controller using JuliaSim control. So I'm going to go ahead and run this code right here. There we go, optimal solution found. So now that we have the optimal controller and we also have the nominal controller, let's do some closed loop validation with the reference system. So the reference system is the system before we've linearized it, right? We just want to see how well the nominal and optimal controllers do against the reference system. So I'll go ahead and run this code right here. And now we can see our validation against the reference system. So first of all, we can see how well the nominal controller does against the reference system. We can see this, this error signal here in blue, and this is similar to what we just saw earlier inside of the GUI, right? This error in blue right here is the same as what we saw right here. Okay, but in addition to the blue error right here, we also have the error against the reference system when using the optimized controller. And we can of course see that the optimized error right here in red is a significant improvement over the error when using the nominal controller. So with that, we can say that we are confident that the optimized controller performs better than the nominal one against the reference system. Okay, so now the next step we want to do, now that we've validated against the reference system, is we want to validate our controllers against the linearized system. Okay, so what I'm going to go ahead and do is just run this code right here. And now on our plot, we see a few more signals. We see how well the nominal um, controller does against a reference system and the linearized system. We can see those signals here against in green and blue right there. But the main signals we're interested in right here is how well the optimized controllers do against the reference and linearized system and if there are any differences. And in this case, we can see that both the error for the reference system and the linearized system when using the optimized controller, their error signals are actually overlap right here in purple. So we are confident that the optimized controller performs well in both the reference and linearized system based on this signal right here, the purple signal right here. Okay? So now that we've validated against the reference and linearized systems, the next thing we need to do is discretize the plant and controller in time so that we can embed or implement a digital controller. So what I'm going to do right here is I'm going to run this code. So the first thing we have is just a simple validation with the discretized system, right? So we can see that the error when using the optimized controller against our discretized system is low. So we've confirmed validation there. And the last thing I want to show you before we move on to the software in the loop validation is the control signal being given off by the controller against the discretized system. Now I go ahead and plot the final control signal, pull out the final control signal value. We can see that the final control signal is a value of negative 8.98. Negative 8.98. That was the final control signal given off in our simulation at a time of 10 seconds. Okay, so I just want you to keep this number in the back of your head. So the next thing we're going to do is we need to do the software in the loop validation. So we went ahead and compiled the controller into a binary and implemented a software in the loop algorithm, and that's what we'll do. That's what we'll perform right now. So I'm going to go ahead and open up a new terminal right here. I'm going to cd into the folder which contains the software in the loop program we'll execute, and then now I'll simply execute that program, which is the PID program. Okay, so in our software in the loop testing, it looks like at a simulation time of 10 seconds, in other words, the very end of the simulation, the final control value returned was negative 8.97. So the final control value returned at the end of our simulation at a time of 10 seconds is negative 8.97. And if we compare that against the final control value returned when we were using the control in our discretized system is negative 8.98. So the difference between the two values we just saw is a difference of 0.1%. The difference between this value and this value is about 0.1%. And if we assume that that error is within our acceptable bounds, we can say that we've completed our software in the loop validation. Okay, so in summary, what we went over today was how we can create models and simulate and analyze them inside of JuliaSim. We then linearized the plant portion of the model to allow for control system auto-tuning and optimization. We discretized the plant and controller in time to implement a digital controller, ultimately enabling software in the loop validation. That concludes my presentation today. I hope you learned something and appreciate you tuning in.